Okay, we're going to talk now about section 15.5, which is factors that affect chemical equilibrium. So we've looked at the equilibrium constant, the concept of equilibrium, and we've looked at doing a set of different types of calculations that we can do for equilibrium. Now what we're going to do is we're going to look at things qualitatively to use something that's a very powerful concept in chemistry, a very powerful technique that we use to produce materials, and that is called Le Chatelier's principle. Le Chatelier's principle is the idea that we can take advantage of chemical equilibrium, the law of mass action, in order to produce materials that otherwise would be difficult to make. And perhaps one of the most famous examples of this is what's called the Haber process. The Haber process was developed by Fritz Haber, a German scientist, a German chemist, during World War I. That was about 1914 to 1918. The issue was that Germany had no easy source of nitrogenous materials to make chemical explosives. They were running out of chemical explosives. So they turned to their chemists to develop a technique to produce more nitrogenous explosives. And ammonia is a starting material for that. Now, the issue with ammonia is that ammonia, the production of ammonia, is through the reaction of nitrogen and hydrogen. And even at very high temperatures, even at 700 Kelvin, the value of the equilibrium constant for ammonia is not very large. It's around 0.3. Okay? So you don't really get very much ammonia out of this reaction. And so using Le Chatelier's principle, there is a technique you can use to produce more of the ammonia, even at the same temperature. Okay? So let me show you a quick calculation that your textbook goes through. What they do is they say, suppose that the concentration of nitrogen is 2.05 molar. The concentration of hydrogen is 1.56 molar. And the concentration of ammonia is 1.52 molar. Moles per liter, right? And suppose we're told that the value of the equilibrium constant is 0.297. Okay? Let's check to make sure that we're actually at equilibrium. Is this a system that's at equilibrium? Remember what you do? You compare Q to K. If Q is equal to K, that means you're at equilibrium. So the expression for Q would be the concentration of NH3 squared divided by the concentration of N2 divided by the concentration of H2 to the third power. So all we need to do is substitute in these three values on the left, and that will tell us whether we're close to 0.297 or not. So let's do that. Remember, equilibrium constants and reaction quotients don't have units. So even though the concentrations are in molar, we're not going to indicate that. So the ammonia is 1.52. So we're going to square that. Then we're going to divide that by the concentration of nitrogen, 2.05, and divide that by the concentration of hydrogen, which is 1.56 cubed, right? Third power. The coefficients become the exponents under the law of mass action. So let's calculate that. 1.52 squared divided by 2.05 divided by 1.56 raised to the third power. And you get about 0.297. So in fact, we are at equilibrium, right? Okay, trivial case. Now, suppose we stress the system. And so what I'm going to do is I'm going to change, we're going to add nitrogen. We're going to add more nitrogen. And we're going to make a new concentration. Okay, the new concentration is 3.51 molar. Now, what we're saying is we're going to open up the container, put some more N2 in there and close the container, or open a valve, pump some more N2 in and close the valve. So now the new concentration is 3.51. Now, let's see what happens. Are we at equilibrium anymore? Is it possible we could still be at equilibrium if we add more N2? Think about the expression. NH3 squared divided by N2 divided by H2 cubed. If we change the concentration of N2, that's going to change the value of Q. So unless the other two values adjust, there's no way we could still be at equilibrium. So let's prove that. So the ammonia is still the same, 1.52 squared. And then we're going to divide that by 2.05. And then we're going to divide that by, 3.51. Let me come back here. Put the eraser on there, 3.51. And then the hydrogen is still 1.56. Okay, so there we go. So now, question, are we still at equilibrium? Hopefully you can see we're not going to be at equilibrium. There's no way this is going to be 0.297 because we just changed one of the numbers, not all three. We didn't even change two of them. So if we take 1.52 squared and divide that by 3.51 and divide that by 1.56 squared cubed, it looks like it's about 0.17, 0.173. So Q, I'll call it Q new, this is our new Q, is not equal to K. Right? Because 0.297 is not equal, well, 0.297, that's K over here, is not equal to 0.173. So we're not at equilibrium. So then the question is, what happens? What happens at this point? Well, think about it. What is Q now? Q is less than K. We have the background to evaluate this, right? We even have the background almost to evaluate it mathematically. See, Q is 0.173 and K is 0.297. So that means Q is less than K, right? If Q is less than K, what did we say in the previous section? The reaction goes toward the products. So here's what happens. Let's put our numbers back in there again. This one is 1.52. This one is 3.51. And this one is 1.56. Q is less than K, so now we'll lose reactants and gain products. And so it'll come back to equilibrium again. And when it comes back to equilibrium, the key here is that ammonia is going to be larger than it was at the beginning. At the beginning, it was 1.52 when it was at equilibrium, but now it's going to go up by some amount, 2x. So what we've done is we've increased the amount of ammonia by adding N2. And that is Le Chatelier's principle. Le Chatelier's principle says that if you're in a system that's at equilibrium, and the initial case we were at equilibrium, where the concentration of N2 was 2.05 molar, by adding more N2, we've taken the system out of equilibrium. And the result of that is the system adjusts through the ice table in order to produce more of the product at the expense of both reactants, so they'll both go down, and you get more of the product. So this gives us an essential technique for producing more material on the product side if the system is undergoing chemical equilibrium. We add more of the reactants, we pump it up, increase the amount of the reactants, and that will result in an increase in the amount of products. That's Le Chatelier's principle. The definitions are variable depending on where you read them. Your textbook says something about adding a stress to a system that's at equilibrium, and then the system will adjust itself to come back to equilibrium. The key to this, however, is that if we increase the concentration of reactants, the result of that will be that when it comes to equilibrium, we will have more products. That's Le Chatelier's principle at work. So the key here is that you definitely want to practice these, as many of them as you can bear, so that you know how to answer the questions. So let me show you the equation again for the Haber process. So the result of this is that if you add either of these, actually either of them or both, this will increase. Now, the opposite of that would be, well, what would happen if you remove either of these, either or both? I'm talking about the reactants. Well, it's the opposite. If adding more of them increases the product, removing them will reduce the amount of product because the equilibrium will shift back to the left. So this will have a result of decreasing the amount of the product. So if there was something about the product you didn't want to have as much in there, one way to do that, to deal with that, to decrease the amount of the product, would be to remove some of the reactants, and that would work. Okay, that's Le Chatelier's principle. So changing the concentrations can affect the equilibrium. Now, there are other changes we can make as well. And so the second change that I'm going to discuss here has to do specifically with gases. It doesn't really correspond to any changes for liquids or solids, but for gases it does. And so what I'm going to do is I'm going to consider a reaction, a more simple equation anyways, N2O4 in equilibrium with 2NO2. If you remember, this is an equation that we've looked at before. We've looked at this reaction. At room temperature, the equilibrium constant is 4.63 times 10 to the minus 3. So that's at room temperature 25 degrees C. Okay. Now, what we're going to do is we're going to ask the following question. These are gases. Suppose we're at equilibrium, and I'm going to give you your concentrations. So the concentration equilibrium of NO2 is 0.1094 molar, and the concentration of N2O4 at equilibrium is 1.286 molar. Okay? Now, oops, sorry, my mistake. Let me come back here. I got the wrong concentrations in there, so that was a mistake. So let me give you the correct one. 0.0547 for the NO2 and 0.643 for the N2O4. Now you can check. Let's see if that's at equilibrium. If we don't know whether it's at equilibrium, we check it. Concentration of the product, NO2 squared, divided by concentration of the reactant, So that would be 0.0547 squared divided by 0.643. Okay. So let's see what that works out to be. 0.0547 squared divided by 0.643. And looks like you get about 4.66 times 10 to the minus 3. That's pretty darn close to 4.63. That's good within a 1 in 100. So we're pretty close. So we're going to say that this is equal to K. Now what we're going to do, we're going to change the volume of the container. So what I'm going to do is I'm going to decrease the volume of the container by a half. So this is our initial volume. And it has all the N2O4s and all the NO2s mixed in together, given these concentrations right here. Now what we're going to do is we're going to compress the gases. We're going to compress this gas mixture. And just to make the arithmetic relatively simple, I'm going to compress it by a half. So now all those molecules that were initially in the original container are now occupying a smaller container. It's smaller by a factor of 2. Okay, so let's write here that V final is equal to 1/2 the initial. Okay, we've decreased the volume by a half. What do you think happens to the concentrations of the gases when that happens? You think about it for a moment. If we decrease the volume, what you're really doing is you're pushing those gases into a smaller volume, so their concentrations will increase. And if we change the volume by a half, in other words, we cut the volume in half, the result of that is we double the volume. The same amount of gases are in half the volume. So that results in a doubling of the concentrations. So the concentrations that we had here at the beginning, 0.0547 molar NO2 and 0.643 molar N2O4, are now double that. And if you double the concentrations, you now have 0.1094 and 1.286 for N2O4. All I did was I multiplied the concentrations on the left by 2. We've doubled both of their concentrations. And now the question is, do we think we might be at equilibrium still? If we change this volume to half of what it was, are we at equilibrium? And the solution to that question is to check these new concentrations. Do those new concentrations give us 4.63 or 4.66 times 10 to the minus 3? If they do, we're still at equilibrium. But if they give us something significantly different, then we're not at equilibrium. So here's what we're going to do. We're going to recalculate this. We're going to use these new concentrations to calculate to see whether we're at equilibrium. So Q, I'll call it Q new. Again, it's the concentration of NO2 squared, our new concentration, divided by the concentration of N2O4, our new concentration. So our new concentration is 0.1094. We're going to square that. And then we're going to divide that by 1.286. Remember, units are gone. And here's what we get. We get 9.31 times 10 to the minus 3. That is definitely not equal to k anymore, right? It's essentially off by a factor of 2. Okay? So q nu is not equal to k. So we're not at equilibrium. In fact, what we can say is that q nu is greater than k. And so the result of that is the reaction goes this way, to the left, right? We learned that in the previous sections, that if q is greater than k, the reaction goes back toward the reactant side. So let's set up a new ice table. Okay. We have 0.1094 and we have 1.286. And we said that q is greater than k, so this is going to go down and this one's going to go up. So it'll come back to equilibrium by losing NO2, and it'll come back to equilibrium by gaining more of the N2O4. So what have we done? We've changed the volume of the container, and as a result of that, we've changed the equilibrium. The system will adjust. This is how it adjusts itself. It undergoes an internal reaction where the NO2 reconverts back into N2O4. So N2O4 goes up and NO2 goes down. Okay? So this is Le Chatelier's principle. We stress the system by changing the volume. We compress the gases. That compression resulted in the reaction shifting to the left, producing more N2O4. So if we saw this occurring, we would see that more N2O4 is produced by decreasing the volume of the container. That's Le Chatelier's principle. Now, we can sum it up for gases by saying the following. This is just sort of a quick little conclusion to this for gases. If we stress a system at equilibrium, again, we're talking about gases, by decreasing the volume. Okay, if we decrease the volume of the container, the equation, or equilibrium, or let's do equilibrium, will shift toward the side of the equation with fewer gas molecules. So in this example, the side that had the fewer gas molecules was the N2O4. There's only 1 mole of gas on that side. Whereas the other side, there were 2. Right? There's 2 moles of gas there. There's only 1 here. So it's going to shift to the left side in that case. So if the equation were reversed, if we had 2NO2 being converted into N2O4, decreasing the volume would have shifted it to the right, and we'd produce more N2O4. Now, what about the opposite of that? Suppose we increase the volume. Increase the volume has the exact opposite effect. Increasing the volume will shift the equilibrium toward the side with more moles of gas. So if we increase the volume, it'll go more to this side, or more to this side in this equation, and away from this side, and away from this side. Okay, so that's their effect. Now again, this only has to do with moles of gases. So if you're looking at an equation where there's solids, ignore the solids. If you're looking at an equation with liquids, ignore the liquids. Just count up the number of moles of gases on each side and then make your comparison. Equilibrium will shift to the side with fewer gas molecules if you're decreasing the volume. Okay? Now there's a third effect that we want to look at, and that's changes in temperature. And so we're going to look at that now. So changes in temperature. All right, so let's take a look at that. Now, this is an interesting thing. It turns out that temperature can affect equilibrium as well. And so if we come back to our equation N2O4, and that's in equilibrium with 2NO2, what's interesting about these two gases is that N2O4 is invisible gas. You can't see it in a container. Your eyes do not, the light doesn't interact with it in such a way that it's visible to humans. NO2, however, is a brown gas. So this gives us a method for determining whether we have a lot of NO2 gas in the container or a lot of N2O4. If we have a container and it's very brown, that means there's a lot of NO2. If it's completely clear, that means it's N2O4. And so here's what happens. It turns out that if you look at this particular reaction, heating this reaction turns the mixture brown. It turns brown if you heat it. Cooling the mixture turns the mixture clear. Okay? So in other words, if you had a glass container, like a closed off tube, and you heated it, so you made it really hot, put a flame underneath it or put it under boiling water, what happens is it turns brown. The gas turns brown. And then if you do the opposite, you put it in a refrigerator, so make it cold, it becomes clear. What that tells us is that if we heat it, it's essentially producing more NO2, because NO2 is the gas that's brown, and there's less N2O4. On the other hand, if we cool it, it turns clear, so that means there's more N2O4 and less NO2. Now, obviously, if the temperature were in between, it would be in between and it would be a little bit brown, right? But we can make it extreme by making it really cold or really hot and see where its color is going to be. Okay? This tells us that temperature has an effect on equilibrium, right? Temperature is affecting equilibrium. In fact, it's reversible. I could put it in the refrigerator and it would turn clear. I could then take it out of the refrigerator and heat it and it would turn brown, and I could go back and forth as many times as I want, which would tell us it's a reversible process. It can go one direction or the other at will. So, if that's the case, what can we say about temperature and the relationship of temperature and equilibrium? Well, it turns out the relationship is a relatively simple one, but it's one that we want to look at. And it's tied into the idea that heat is related to something called heat capacity times the change in temperature. So if we increase the temperature, there's a delta T, right? The final temperature minus the initial temperature. What we're doing is we're really adding heat. By increasing the temperature of something, we've added heat to it. By decreasing the temperature of something, if delta T is negative, so we're decreasing the temperature, we're removing heat from something. So if I take this glass container and I put it in a refrigerator, really what we're doing is we're transferring heat away from the gas. On the other hand, if I put it in an oven, what I'm doing is I'm transferring heat in from the oven. The oven is transferring heat into the into the gas, into the mixture of gases. So we can put heat in or we can put heat out. And it turns out there's a property of gases related, or a property of materials that's related to heat, and that's called enthalpy. And the enthalpy change, which we'll call delta H, is essentially the amount of heat that's being transferred in a process. So if heat goes into a material, the enthalpy change is positive. If heat comes out, then the enthalpy change is negative. So here's the way we analyze Le Chatelier's principle in terms of temperature changes. If we add or increase the temperature, which we'll call T, we're adding heat. If we cool the sample, so that's decrease T, then we're removing heat. Okay? Heat's going down. So we can use that to analyze Le Chatelier's principle and how it relates to temperature changes. And here's how we do it. The fact that increasing the temperature of this mixture produces more brown gas, right? So if the temperature increases, the result of that is you get brown, which is NO2. And if you reduce the temperature, the result of that is that it's a clear gas, which means you're producing N2O4. Tells us something about the reaction itself. What it tells us is that adding heat drives the reaction to the right. And so we can write that in the following way. We're going to write delta H plus N2O4 produces 2NO2 gas. The experiment that says that if you heat the gas it turns brown tells us that there is essentially, we can treat it like a reactant. And we're going to put the reactant on the left side. If we put the reactant on the left side, that means that we need heat for this reaction to go to the right. And so we call that endothermic. We would say that's an endothermic reaction. So by doing these experiments, we can determine whether a reaction is endothermic. We can also determine whether it's exothermic. Okay? So suppose that I did the opposite. Suppose I wrote the equation in this way. There's nothing wrong with doing this. It's arbitrary which one we call forward and which one we call reverse. In equation 1, we're calling the forward reaction this one and the reverse this one. In equation 2, we just reversed it. So this one's now the forward and this is the reverse. So what would we say about this? Well, if this reaction here, reaction 1, is endothermic, then this one would have to be the opposite. And we would write delta H on the product side, and we would say that this is exothermic. In other words, if we add heat to equation 2, if we increase the temperature, it's going to drive the reaction to form more NO2, which is exactly consistent with increasing heat in reaction 1. It's just a matter of which way we want to write the equation. So let me show you the other example that's in your textbook here. The reaction we're going to look at here is occurring in water. So this is not gas phase, this is occurring in water. And the reaction is what happens if we take cobalt chloride in water and we react it with water. So that's easy to occur because it's in water So there's certainly water to go around, right? And this is going to give us COH2O6, 2 plus 4Cl minus. Okay? Now here's what's significant about this reaction. This is why we pick it as an example. It turns out that this substance on the left in water is blue. And this substance over here on the right is pink. So cobalt chloride is blue, but hexaaqua cobalt 2 ion, that one's pink. Water, of course, is clear, so is the chloride ion. So suppose we do the following. Suppose we increase the temperature. So we have a mixture, this whole thing right here. It's all in water. Okay? And so it's in a test tube. And we increase the temperature. Okay? And it turns blue. Then what we do is we say, okay, let's see if it's reversible, and we go back and we decrease the temperature. And it turns pink. Okay? Let's see if I can find some pink here so we can illustrate this. So over here it's blue, pink, and then over here it's blue. So the first question we're going to ask is, on the left, where it's blue, what is the dominant material in terms of the cobalt? Is it mostly cobalt chloride, or is it mostly hexaaqua cobalt 2? It's blue, so that means it must be mostly cobalt chloride, right? So that tells us that we have mostly COCl4 2 minus. Maybe not 100%, but mostly. And then on the right, it's pink, so that means we must have mostly hexaaqua cobalt 2 ion. Mostly. So at the increase in temperature, so that's high temperature, this means we added heat. It's blue, that means we have cobalt chloride. And then on the right, we decrease the temperature, so we removed heat. And that's why we get the cobalt, the hexaaqua cobalt ion. So here's what we do. We ask the following question. Is this reaction, as it's written, endothermic or exothermic? That's the question we ask. And generally, when you look through problems, that's what you're going to be asked. Is it endo or exothermic? So if we take a look at it, how do we describe that? We're either going to put delta H on the left side, on the reactant side, or we're going to put it on the right side, the product side. And what you do is you try either one and see if it's consistent with the experiments. These are our two experiments right here. If we put delta H on the left side, so over here, okay? If it's a reactant, what would happen if you heated it up? Heating it up would be increasing delta H. Well, that's a reactant, so it should drive the reaction to the right, and you should get more pink. Okay? So let's see. Increase the temperature, and it turns blue. Okay, well, there you go. Nope, that's not right. Increasing the temperature, if it's a reactant, should drive the reaction to the right, and it should turn pink. So that can't be right. Can't be an endothermic reaction. So delta H is not over here. So let's try the opposite. Suppose the delta H is on the product side. We call that exothermic. Heat is released in the reaction, so it's a product. Okay, well, if it's exothermic, then increasing the amount of a product should drive the reaction in the opposite direction, and it should turn blue. Well, that is what happened. Increasing the temperature turned it blue. Okay, well, what if you remove some of the heat? You cool it. You put it in the refrigerator. That's decreasing the amount of this, so the reaction should try to replace it and go back in this way. It should turn pink, and that's exactly what happened. Okay? So our analysis, our result here, just to sum this up so that you can do the problems, is that if you heat a sample and it's endothermic, meaning delta H is on the reactant side, you should produce more product. If you cool it, it should produce more reactant. And if it's exothermic, which was our second example, the one with the cobalt, then if it's exothermic, then heating it should produce more reactant. And cooling it should produce more product. Okay? So we're treating delta H, the symbol delta H, if it's endothermic, you're treating it like a reactant, just like we did in our discussion of the effect of concentration. And then you're also using delta H as exothermic. If it's exothermic, you treat it as a product. Okay? So that's Le Chatelier's principle. Hope you find it interesting. It's an important aspect of chemistry.